Today we are looking at our next unit, Unit 7, Multiplication and Division Problem Solving. And there are 3 TEKS in this unit that we're going to talk about today. The first one is 3-4K, where students are expected to solve 1- and 2-step problems, where there's multiplication and division. We're working within 100, and we're using strategies based on objects, pictorial models, including arrays, area models in equal groups, properties of operation, or recall of facts. That means that when we're presented a problem like this, where there's no specific image given or anything other than a word problem, the student holds the decision-making power about what strategy they're going to use. So I don't get to tell a student, you have to do X, Y, Z. I can say, I would like to see some kind of a picture drawn. That leaves it up to them of what kind of a picture. Maybe their picture is a strip diagram. Maybe it's vases with flowers. Some sort of a model. I can ask for that. But I shouldn't be requiring a specific thing for students to do when they are given the option in our standard. So I picked a few questions for us to look at today. I picked the 2021 question, a couple of them, because I want us to look at the data and see that, not only across the state could we look at this and say, wow, students really didn't know what to do with this problem, but I want us to look and see that Goose Creek's data really mirrored the state very closely. So we're in a situation where we've got to figure out, how do we help kids with this type of a problem? What is it that's going wrong? So we know that the majority of the time, this standard is going to be tested with multi-step problems or 2-step problems, not just a 1-step problem. So let's talk about what are some models that would work. I know that it's probably not the most popular thing to say that we should be drawing strip diagrams for every problem. Because some problems, let's face it, that's not necessarily the easiest thing that they can do. But the more we model that part, whole, and equal parts, the more students will make sense of it. So that's what I want us to look at. So if I start with this problem, and my expectation is that students take this problem and break it up into parts, the first thing I would do is say, okay, Miriam had 63 flowers and 9 vases. That's good information. However, she threw away 9 of the flowers. So if I'm trying to figure out what to do with that information, that's a part, whole model. So I know we started with a total of 63 flowers. And what happened to those? 9 got thrown away. I need to know how many are left. 63 minus 9, I know that already. It's 54. So now I know step 1, she threw those away. She has 54 left. What does she do with the ones that she had left? Well, she took those 54 flowers that she had left and she put an equal number into each vase. So here's where we can draw a second strip diagram and say, if we had 54 flowers left, how many vases did she break those up into? 9 of them. I don't know that I can draw 9 equal parts on here. We're going to see how lucky I get. 1, 2, 3, 4, 5, 6, 7, 8, 9. Very good. She had 9 vases, so each one of these, I have to figure out how many flowers went in each one. So that's 2 ways I can, 2 strip diagrams I can use to model what's going on in this problem. And we know that 54 flowers divided up into 9 vases is 6. Now, the second way that we could see this tested, besides a strip diagram, is with equations. So I realize that in this particular standard, equations isn't listed up here, but this is a problem that we could use for 3-5B, where we represent with equations. So we could expect students in this unit to do that with each problem that they do. The more they do that, the more comfortable they would be. So if I think about what math did I do to solve this problem, I know that I started with 63 flowers, 9 got thrown away, and I was left with 54. Then I took those 54 flowers, divided them up between 9 vases, and I had 6 flowers in each vase. So we've seen STAR questions before in 3rd grade where we're given answer choices where there are 2 equations as one answer choice. So F might say these 2 equations for this answer choice, 2 different equations, to see, do kids understand the steps? In 3rd grade, you won't see this problem solved with one equation because I would have to know how to use PEMDAS, or order of operations, to do that correctly, and that's a 5th grade standard. But you could see it with 2 equations like this. So let's look at the next one. This is also 3-4K, and it's also 2021. So here we can look and see that, again, we mirrored the state pretty closely with our data, and it's interesting to me that other than the correct answer, the most popular answer was A, which was just 33%. And 33% of our kids decided I should just take the number of games plus the number of red balls plus the number of green balls to figure out the total number of balls that he threw. That bothers me because we would never say, if I played football, I add up the number of games I played in a season plus the number of times I threw the ball plus the number of times I kicked the ball to see how many points I scored. That's not how you solve that problem, which means our kids aren't making sense of what's going on in the problem. Unfortunately, I think that some of our approach to our problem-solving model has caused this. We've taught kids, do you have a total or are you looking for a total? And unfortunately, if we're not doing that in context, then we're setting kids up for some big mistakes, because kids look at this and say, oh, they're asking me for the total. And then they say, oh, I don't see equal groups, so I must have to add them up. So this is an adult-created problem. We can't use that, do you have a total, are you looking for a total, as some magic formula for how to solve problems. We have to use it in the way it was intended, and that's to guide thinking. The thinking involved here is, I am looking for a total, but a total of what? A total of the number of balls he threw. Well, what do I know about the number of balls he threw? Well, I know that every time he played a game, he threw 4 red balls and 3 green balls. And he did that 14 times. So I could say, I don't know the total. That's what I'm trying to find out. But I do know 14 boxes. Let's see. I might have to make this. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. We're going to make those last ones small. 12, 13, 14. I do know that there were 14 games, and every game that he played, he threw the ball 7 times. So do you see how this strip diagram could help me? Then I can look at it and say, okay, 14 times 7. Or I could see equations. I could see 3 plus 4 equals 7 times that he threw the ball every game that he played, 7 times, 14 games, 98. So I really need us to be careful how we're using that, do you have a total or are you looking for a total conversation. We can't teach kids that when they see that I'm looking for a total, I either add them or multiply them, because in this case I had to do both. So we have to be really careful how we're presenting that to kids. Okay, so our next TEK in this unit is 3.5b, which is represent and solve 1- and 2-step multiplication and division problems within 100 using arrays, strip diagrams, and equations. And I picked this problem to talk about because of the data. If I look at this comparison over here between the answer choices, this tells me we really had no idea what to do. because there's just way too much variation between this. Only a third of our kids had any idea that the answer would be B. Look at how many kids didn't get it. We had a big chunk pick A, a big chunk pick D, and too many picked C. So there was just no real understanding of what to do here. I can guess a couple of things that might have happened here. I feel like maybe this threw some of our kids, because we didn't talk about what half is. Half of 6. That might have thrown some of them. And what does it mean when we take half of something? It means we're dividing it up into 2 equal groups. So I need to see something that's dividing things into 2 equal groups. So how would we model this? Well, we have equations, and we know the answer is B. So we know that we had 11 packages. There were 6 balloons in each package, so there's my equal groups, 11 times 6, and then divided by 2 because half of the balloons were red. So I get that, but how do I model it? So there's several things that I could do. I can tell you what I think kids would do is draw 11 and start by labeling them. There's 6 in every package. Right? So now I know how many balloons are there. Well, there's 66 balloons. Okay, that helps me a little bit, but I still have this other piece of information here. Half of the balloons in each package were red, and I really only care about the red ones. So what could I do here? Well, I could go back and say, I don't want all of these 6. I want 3 out of each package. I'm dividing this by 2. So if I only want 3 out of each package, then I've gone through and said, I'm going to take half of that package, and it's going to equal 33. So I have to give kids an opportunity to interact with these kinds of problems and make sure I'm putting this academic vocabulary in front of them and talk about what does that mean with math? What does it mean when I say half of something, right? So I think that's probably what got us on this one, and we probably need to just make sure we're putting that vocabulary in front of kids. And here's the trick, guys. If we aren't drawing pictures of every problem that we do and talking about equations for every problem that we do, we can't expect our kids to understand how to do that on their own. And then they do, unfortunately, go to those things that we really hate, where they draw all these circles and then put 6 dots in every one of them. And so we've got to move them towards something more efficient. Okay, one more to look at on this video, and that's 3-5D. That's where we're using what we know about multiplication and division facts to find a missing piece. And I chose an old question. This is a 2015 question. You can see over here that we don't have any data on it. That's because it was a sample question. So I wanted us to look at this because it's not necessarily a fact that they would just know. So this is where we've had to make that connection with our students about the relationship between multiplication and division. So as I've taught my multiplication and division facts and fact families, then I've presented to kids that multiplication and division undo each other. They're opposite operations. They're inverse operations. And so if I have a division problem and I'm trying to find a missing piece, my missing piece, I use multiplication. If I have a multiplication problem and I'm trying to find a missing piece, I use division. So we simply say the opposite of this would be multiplication. If I'm trying to find this out, it's like saying there was a bunch of something and I broke it into 3 equal groups, and that put 13 in each group. So how do I figure that out? Well, if I have 13 in each group and there are 3 groups, then I can multiply to figure that out. It helps them make that connection between the relationship with multiplication to addition, multiplication facts to addition facts. And we have to tie it beyond just the basic facts that are in our automaticity teak. So we want to tie it to what's the relationship between the 2 operations. So again, 3 big teaks in this one. This unit is your opportunity to really mix up the problems. We've already taught multiplication in isolation. We've taught division in isolation. Nothing else we do the rest of the year should have those operations in isolation. Everything else should be mixed practice the rest of the year. So not just in this unit, but as we continue to spiral it for the rest of the year, mixed practice. We're not doing just multiplication today and just division tomorrow. It's all mixed practice from here on, because I've built that conceptual understanding so kids can know how to recognize in a word problem, what is it asking me to do? Multiplication, division, single step, two-step. Is it multiplication with addition, multiplication with subtraction, multiplication and division? There are lots of combinations that we can make, but we're doing one and two-step problems, mixing up the operations so kids don't get the idea that, oh, today we're only doing multiplication. I'll just pull out the numbers and multiply. Okay, let me know as always if you have questions or if there is anything that you need.